So as Hugo already said, my perspectives probably compared especially to the first three presentations will be a rather global scale. It has to do with the species I present of. So I will start by just showing you this very simple approach. In my presentation I will go from really like a global, really sleep duration view to the structure of sleep, and then zoom into slow waves and more electrophysiological characteristics of sleep. And the goal is basically to show you that maybe development can be a very interesting approach to investigate some of these very basic research questions we still have in sleep. So what you see here basically is on the left side here is sleep duration. And I would just like to highlight that you have a huge decrease of sleep duration, as you all know, which goes along with the equally dramatic head growth, as you can see on the right. I think one peculiar thing I would like to highlight is basically the huge variability you have during the first year of life. So how can it be that about 2% of our infants need to sleep only about 10 hours, whereas another 2% up here on the 98th percentile need to sleep more than 18 hours. So it's a huge difference of the sleep need these infants have. And still, later on, there's a considerable variability in sleep duration there. I think this is an important feature we need to understand, and behind that is really the question why sleep need is so high during childhood. I don't have the definite answer to that, as you will see in the course of my talk. For historical reasons, I think it's important to highlight also this, the issue of REM sleep, which, as you can see in this graph very nicely, is really very prominent during this this first year of life, where more or less half of sleep is spent in REM sleep. Probably also led to this hypothesis, or this seminal paper by Rothwark, the ontogenetic development of the human sleep dream cycle, which definitely caused a lot of impact in this field of sleep and development. And it fits very nicely to this observation that basically the amount of REM sleep is very closely related to the developmental status at birth. So you can see the guinea pig, which gives birth to really quite highly developed infants, has very little REM sleep from the beginning, whereas the rat and the cat, where pups are very immature when they are born, have very high amounts of REM sleep. So it's just an observation that there's this very close relationship between REM sleep amount early on and the status, developmental status at birth. So let's go from this more structural sleep structure view and zoom into what's going on during slow wave activity. And this is a graph which has been presented numerous times. The first important part is if you focus on slow wave activity here in the reddish, you see that we have an increase of slow wave activity before puberty and then a dramatic decline during adolescence. And a very similar trajectory can be observed for synaptic density here in yellow-orange, or energy consumption in green. And we even have some MR non-invasive methods to investigate that. If you focus here on these MR images, in white you see gray matter, here of a young child, and here of an adult. You easily can see this dramatic reduction of gray matter volume, which goes along with this decrease in slow wave activity. So this is just an observation, has been found also in the rat, where very similarly you have this increase of slow wave activity and a decrease during adolescence. Of course, the big question here is, do these slow waves play an active role, or are these just phenomena which happen in parallel and show a similar trajectory? I think this is still unanswered, but is certainly an important question. I think if we zoom in from this more trajectory on a global level and go and look locally, we see even another interesting pattern. And if we used high-density EEG to investigate the development of the topography of slow activity, we found that in contrast to what we have known from adults, that the predominance of slow activity is situated over these very occipital cortices in the very young child. And then over time moves to the center and finally reaches this frontal predominance we know in adulthood. And this is interesting because we know that also the cortical cortex height matures, starts roughly on the back and moves to the center and finally reaches frontal cortices in the late 20s. So maybe again we see this very parallel development of slow effectivity and cortical maturation. Of course, we were wondering what is this also related somehow to these use dependencies you have heard before. So if we challenge or if we deprive a certain area, we see that there are more slow waves produced later on. If we subject a certain area to a learning paradigm, as we did in this task, it has been shown before that more slow waves are present during subsequent sleep. We did that in children, adolescents, and adults, and indeed found that after this task, we found a local increase over this right parietal area. Now, if we looked more closely, we saw that this local increase was much more prominent in our children compared to the adolescents and the adults, maybe reflecting really a critical, vulnerable period when you subject them to the very same task, the very same learning task, that they react with a much stronger local increase in slow activity compared to adolescents and adults. So this just shows you again, and actually we were even able to relate that to a maturational marker, an anatomical maturational marker where the volume of the right parietal cortex, this area, was related to this local increase in slow activity during sleep, and was not related, for example, to the volume of the left parietal cortex. So it seems to be really specific determinant of the developmental status of a specific brain area. So the question, of course, here is, again, do these local changes in slow activity just reflect some sort of a maturational process, or does this interaction, this relationship between learning and the local changes in slow activity benefit maturation in the long run? Of course, we haven't addressed these studies so far. But what we have done, and I think is really interesting, we used these very same tools and looked into psychiatric disorders, early onset psychiatric disorders. Here you see kids with attention deficit hyperactivity disorder. And what we find basically is also quite dramatic local changes compared to healthy controls, namely an increase of slow activity over these very central regions and rather a decrease over prefrontal cortices. And it looks quite different if you go into early onset affective disorders. So here you see adolescents, 15 years of age, with the major depression, and they basically have the opposite. So they have more slow activity over frontal cortices and less so over central areas. The big question here, of course, is this a maturational or a use-dependent change? So is this really because they are lagging behind in maturation, as for example, there is a hypothesis about that for ADHD, or are these just use-dependent changes? Let's say you are hyperactive, you use more your motor sensory system more, and that's why you show more slow activity over central regions, as we've seen in ADHD. We don't know. I think one interesting aspect about slow activity and its regulation is also shown in this example here, where we looked into minimal conscious patients, very young, who had sort of a left eye field perception remaining. And if we look at the regulatory aspect of slow activity, we see that there's hardly anything going on. So you see here the first 30 minutes of non-REM sleep. You see here all channels we investigated. And you see that most of them are really low here and stay low throughout this time. But there are a few channels which show a nice build-up, which we sort of interpret as some minimal regulatory aspect remaining. And if you localize them, they are exactly over this right visual cortex, which fits very nicely to the patient's remaining abilities. And I think this looks very different if we go into power, because there, in addition to this spot here, we see also other spots coming up where power is very high. You see these channels here, but it seems not to be regulated. So I would say that the regulation of slow effectivity is a very important aspect to investigate, and might be completely different from this non-regulated slow effectivity. Another aspect, yes, 30 seconds. Is really this homeostatic regulation during development. I think also here you can see that what we did is, if you, in a homeostasis, you should have a balance of slow effectivity across 24 hours, which is not the case at all in this, at this early stage. Because if we quantify early on, we see that they have a gain of slow effectivity across 24 hours early on, and a loss of slow effectivity across 24 hours later. And so we don't understand why we have this huge shift in gain and loss across developmental status. Let me switch this and just come to the conclusion. So what I try to show you is why we have so high sleep needs during development, and what's the specific role. Does sleep play an active role during maturational process? And if I summarize this, basically what it boils down to, I think, is if indeed sleep is not playing an active role during development, why do we have these rather dramatic changes in sleep amount, sleep structure, topography, and trajectory of slow effectivity across development? With this, I would like to acknowledge all the people and the funding sources, and thank you for your attention.
Thank you, Reto. Questions?
Thank you. Well, my first question is, do you have other patients, like the MCS patient that you've shown? Like, is this a consistent pattern?
Yes, we have others. Of course, it relies a lot on how good can you quantify function in these patients, as you know. But we have a few others, and it seems to match pretty well. I mean, I also have to admit that if you compare that to the regulation in a healthy subject, you know, it's a factor of 10 difference. So this is really minimal regulation which is left.
I see. And then can I building up on your last point in this conclusions, longitudinal measurements, are there any longitudinal measurements, be it in animal or humans, where you assess cortical excitability by perturbations, meaning peripheral perturbation, somatosensory perturbation, visual perturbation, cortical perturbation, electrical, whatever, to track changes in excitability over time in development?
There are a few studies where people have used auditory evoked potential, and they show actually quite dramatic changes in amplitude, which go along with this. But more than that, I don't know. But it's certainly something we should do, combine this with other measures.
One thing, since we are talking about neuropsychiatric disorders, to get out of the panel autism, if someone in the public has a question, please raise your hand, and we will open the session to questions from the public, considering that we are also handling human studies that are prone to questions, so we can get out of our autism somehow. Questions?
Yeah, I'm always been curious about REM sleep in infancy. So I'll ask you, like, in Australia, is that really REM sleep, or is all the characteristics of REM sleep autonomically wise and just good?
Yeah, that's a very good question. I mean, if you have ever scored or looked at infant sleep, of course things look very, very different. So from an electrophysiological point of view, you can differentiate active and passive sleep, as often this is called. But whether really it shares, of course, also some other characteristics like rapid eye movement, things like that. But from an electrophysiological point of view of the brain waves, it looks quite different. I mean, it's very clear, for example, that you have much more slow waves also during REM sleep during these early years compared to later on, where you really have a more stage 1 or wakefulness-like feature. So I agree. I'm not sure. This is the classic definition according to rules, but there might be more to it than that. Yes.
Can you please comment on one of the issues you were raising in the last slide? What kind of causal manipulation do you foresee could be used on humans to test some of your hypothesis? Because I think it's a big technological challenge.
Yeah, I agree. I think, well, yeah, that's why I think this is one of the important issues, and we're working on it hard. So we're trying to use some stimulation paradigm, trying to manipulate slow waves throughout the night locally. I mean, that's our goal. So our goal is to really use, as Born study, for example, showed these closed loop stimulations, you can use to really trigger or boost slow waves, and potentially you can also use it to deprive it, and use these kind of approaches to see how this affects, first of all, homeostasis itself. So do you need some more recovery sleep the next day in this local area, but also does it affect behavior? So that's an approach.
But if you were to plot this topo maps of the wake energy across development, focusing on some specific relevant frequency like theta or alpha, do you see anything interesting there as well, or these developmental changes are really about sleep and slower?
Yeah, we haven't looked at that carefully. I think it's an interesting point. I mean, of course, you have to be careful what kind of frequency ranges you're looking at during wakefulness. Of course, and what kind of wakefulness you look at. As we discussed before, if you do quiet wakefulness, eyes closed, look into the alpha range, we know that you have this predominance of slow waves, so of alpha waves over occipital cortex. It's the case in adults. It's the same in the kids. But other frequency ranges we were looking at is more theta related, and I think there we have some evidence that this matches more closely to what we see in the slow waves during sleep, which could be interesting. Especially we see that in the evening where sleep pressure is very high in these kids, and they produce these huge theta bursts. And if we topographically look at them, they show some similarity to the distribution of slow waves during sleep thereafter. So that might be an interesting aspect.
Good. If there are no more questions, I'll move to the last speaker so we can catch up some time. And the last speaker